Today, we have Bo Dai, a research scientist with Google Brain, who will be talking about representation-based reinforcement learning. Bo is a staff research scientist in Google Research Brain team. He obtained his PhD from Georgia Tech. His research interest lies in developing principled and practical machine learning methods for reinforcement learning. He is the recipient of the Best Paper Award for AI Stats and NURI IPS workshop. He regularly serves as area chair or senior program committee member at major AI ML conferences such as ICML, NURI IPS, AI Stats, and ICLR. So without further ado, Bo, we look forward to your presentation.
Thank you. Thanks for the introduction. And since I only have one screen and I don't see any, once I share this slide, I don't see any feedback from the chat. So if you have any questions, just interrupt me and ask the questions. Okay, thank you. So yeah, today I will present our recent work along the representation-based reinforcement learning. Actually, this is a joint work with Tong Zheng from UT Austin, Tianjun from UC Berkeley, and Sherry is from, and Lisa from Google. Na it's for professor from Harvard, and you guys are definitely familiar with Dale and Chaba. Okay, let's start. This is the outline of today's talk. First of all, I will discuss some difficulty in model-free and model-based reinforcement learning, which basically is our motivation to look into this kind of representation-based reinforcement learning. And later we will introduce our first work, actually, which is the origin of this line of research, which we kind of like use infinite dimensional linear representation for nonlinear model, for reinforcement learning with nonlinear model. And later, because the success of this kind of research, we further improve it to see whether we can use finite dimension linear representation to refine the results. Okay, let's start with the first part. I think this slide is just trying to give some background about the Markov descent processes. And to be clear, I don't think it's necessary to introduce it here, but just for the notation consistency, I will just present here. So basically, this work is based on this work is trying to figure out the reinforcement learning based on Markov descent processes, which would it's usually defined as a tuple, where the S stands for the state space, A stands for the action space, and the reward function is the mapping from state and action to a real number. And the transition operator actually is a conditional probability, which means I give you the state and action. It goes to next state with some probabilities. And later we denote mu as actually U as a initial state distribution. And with that, we can define the value function, V function here, which basically is doing the accumulation of undercurrent policy and the transition operator to accumulate the reward function here. And similarly, we can define the state and action value function, well, which usually denoted as Q. And later we say a policy actually is also a conditional distribution, which means I give you current state S. It provides a distribution over the action space. Okay, here's the definition of the MDP. And then we discuss the first part, which is the difficulty of the model-free and the model-based reinforcement learning. Let's first see the model-free reinforcement learning. Basically, current model-free reinforcement learning are usually categorized into two classes. One is the Q-based, value function-based learning, and also the other one is policy-based learning. We know that Q learning actually is doing the stochastic dynamic programming based on the Bellman equations, which I list here. And the policy gradient actually is proposed by Rich, which is directly parameterize the policy. While when you do the update, you calculate the gradient with respect to the parameter of the policy and iterate, update the policy, and so on and so forth. And I think we know the benefits of this model-free reinforcement learning is that it is very easy to incorporate the a popular function approximator like deep nets and so on and so forth into the algorithm, so that we can, without any painful, to incorporate any new construction of new architecture of the deep nets for better performance. And we already witnessed a lot of success in this category, for this category of algorithm in practice. But there are actually some difficulties in applying this thing into real cases, because once you introduce very complicated function approximators, it is difficult to capture uncertainty, which means it's not easy to do the exploration based on the uncertainties, and in a principled way. So actually, we notice a lot of algorithm actually is trying to do the exploration by many heuristic designed intrinsic reward to such kind of stuff. It is good, but still, it's not very principle for us to provide the theoretical guarantee for that. And another category of the reinforcement learning is model-based reinforcement learning. Let's see a very simple cases, which is called a linear quadratic regulator. Linear because the dynamics in this model is linear. We can see here. The next state. I just used the notation from the control community. Okay, actually here S corresponding to the state. So you see this dynamics is basically linear, and the U here is action. And the object function is quadratic with respect to both the state and actions. And in control community, if the model basically here is Q, R, A, B, and S is given, we can solve this optimization with efficient, elegant, with the efficient algorithm, and the analysis is also provided. But practically, we don't know the model, so we need to collect the data and then estimate the linear dynamic model and also quadratic reward, and apply the algorithm to solve the LQR based on the estimated parameters, and then use the use the learned model to collect the data and so on and so forth. This is practically we use it. But actually, it's not the case, because we don't know the model. Sometimes if we don't do the exploration enough, we may stuck in a suboptimal policy. So in practice, we need to also introduce some exploration step in when we want to solve the LQR, which is usually is UCB based. So it is good in terms of the statistic guarantee, which means we can have a regret bounded by square root of t. But it's once you introduce such kind of UCB bonus into it, the optimization is no longer convex, which means the object function is not only quadratic, actually it have the actual bonus in that. So that means we cannot use the existing LQR solver to solve that anymore. So this is only for linear quadratic regulator. But practice, we know the dynamic is definitely not linear. It will introduce some nonlinear component into it. That will give some trade-off between the flexibility versus planning tractability. And we definitely know the model usually is unknown. That means we need to take care of exploration versus exploitation trade-off. So these things actually makes the model-based reinforcement is not that easy to use in practice for a real problem. So then the nature questions we want to ask actually is there any way we can share both benefits from model-free and model-based reinforcement learning through a practical algorithm with rigorous theoretical guarantee? Yeah, I know there's a lot of requirement. The answer is yes. But before that, let's first see a pioneer along this line, which is Dinah, provided also by Rich. It is trying to combine the model-based and the model-free reinforcement learning in one algorithm. the idea actually is quite straightforward. We can see during the estimation stage, we are not only estimating the model and the reward, we also learn a function Q through the TD learning, a TD update with real sample. And then we get a sample from the learned model, to refine the Q function. And we use the Q function to collect the data and do the iteration, so on and so forth. Actually, this algorithm is quite good because it's explore the model-free reinforcement learning to heal some problem of model-based reinforcement learning, which specifically is when we have the nonlinear dynamics, we don't know how to plan with it. So we use Q learning to find the optimal policy with that model. Meanwhile, because we introduce this model specifically to the model-free IL, we can use the model to generate some simulation data for data augmentation. And we know data augmentation sometimes is very powerful. Another benefits of that is that we can introduce the reset part to avoid the exploration of the whole trajectory. We can go anywhere we want to help the exploration. It seems this model, actually this algorithm is quite powerful, but I just want to ask this question. Is this the final answer? The answer is definitely no, because in Dyna, there's still some difficulty because of the model-free component and the model-based component actually are independent parameterized, which means the model and the Q function, specifically in the Dyna, that doesn't share any component in it. This kind of separation actually leads to the difficulty of we don't know how well the Q learning is performed for planning. Meanwhile, it's difficult for us to design a theoretical guaranteed exploration. Okay, so actually this motivates us to see whether we can have a better algorithm to combine the model-based and the model-free IL together. Basically, we want to answer these questions. Whether we can find a practical algorithm with theoretical guarantee while still bypass the difficulty in model-free and model-based reinforcement learning. And the way we handle it is by representation-based reinforcement learning. Yeah, essentially, we find a function space such that it can both represent the Q function and also play a role in the model based reinforcement learning. And until now, I think I present my motivation, and I was wondering whether there's any questions from the audience. Okay, sounds good. Then I will go to next component, which is actually origin from our idea. Let's see. Actually, at the beginning, I just checked this model to see, okay, we want to generalize the LQR. Compared to LQR, this model no longer handles the linear dynamics. We have F function here. F can be arbitrarily complicated. So for example, neural network. And then we also have a arbitrary reward function here. Is it possible we solve this one even we give the model? We check literature, the answer is no. So it's a little bit disappointing. So even a very fundamental problem without learning, it seems like not solved yet. And suddenly I realized it is potentially we can do it because we can rewrite the transition dynamics as a Gaussian distribution by this noise. This noise actually is Gaussian, so we can rewrite the transition dynamics according to the transition operators like this. Okay, and then here actually it's a very very preliminary trick used in kernel community, which is you can always use because it's Gaussian kernel, so we can always return the Gaussian kernel into two Gaussian inner product in RK-chess space. Here K is a Gaussian kernel, and F is just this F plugin here. Basically, this is just to do some manipulation or algebra manipulation. It's easy to get this. And we can also rewrite this into an infinite dimension multiplication by random feature. So this is a very common trick. I mean, how many? At least 15 years ago. Okay, with this formulation, actually, we can connect this complicated stochastic nonlinear MPC problem to linear MDP. In another way to put it, once we can factorize this transition operator into this linear relationship, and also we assume the reward function also lies in this, represented by this phi feature, we can have this relationship, which means the value function, the Q function can be represented by this phi. The proof actually is very simple. This step is follow the Bellman recursion, and we expand the linear representation of T into it, and we have this inner product formulation. And also we know R lies in the phi space. So essentially we can rewrite the Q function we can rewrite the Q function with respect to phi and weights. Okay. Now with this property, actually it's very good because it tells me that if I have a very complicated stochastic nonlinear model, I can still use a function space to represent all the Q of Q for each pi. And therefore, I can do the Bellman update, a Bellman backup in this function space. Okay. And also it's linear, so it's very good. Until now, we can say with this kind of structure, we can do the dynamic programming, use the phi function specifically in with linear update in this space. So I think this is very important in my whole talk. I was wondering whether there's questions about this.
Sure, I'll ask a question.
Sure.
As you know, we've looked at a system called linear dyna, and we basically you're saying, oh, if your feature representation enables you to make a linear model, then it's simpler. So it's an important special case, but it's extreme special case. Is there anything more going on here other than saying, suppose my feature representation is enough to represent things linearly?
I think I want to emphasize here, I didn't say a special feature. I'm just saying for arbitrary dynamic with complicated F, it could be neural, whatever. I can find a subspace, linear space, to represent its corresponding Q function.
Well, it's always theoretically possible for any complicated function you can represent linearly if you have arbitrary features, right?
Yes, and I finite. That's the point. So let me specify what is it. What is it? This is my dynamic function, and this is Gaussian kernel. Essentially, conceptually, it is infinite dimension, so it's not computable. So we rewrite it into a random feature formulation. Essentially, this part is the linear feature in which space we can use, in which space Q function is representable. If I rewrite it concretely, it is F plug into here as X, so it's cosine omega transpose F and cosine omega sine omega transpose F, and omega is a random vector sampled according to a Gaussian distribution. So it's basically a random Fourier feature based on the dynamics.
Well, I'm not sure I understand all that, but you know, an arbitrary system, you can only represent linearly if you have an arbitrarily large number of features.
Yes, I agree with you, and that's the point. And if you say that, I would reply that we find a specific way to construct such kind of feature to represent it linearly. Yeah.
Well, I haven't seen you, or maybe you do think you're offering what the features should be. Do you think you're saying what the features should be, or you're just saying there could be such features?
That's really good questions. I would reply like this. I find one way to construct such feature to linearly represent my Q function. And
so you are finding the features.
Sorry?
You're not just saying the features exist, you're saying you have a way of finding them.
Yes, I have a way to construct it in this way.
Have you told us that way yet, or is that still to come?
This is the way I construct it. This is Gaussian, so I factorize it into inner product between two components.
Do you know F?
Yes, I know. This is for this moment, I do a planning part. I'm trying to solve a planning problem. So I know F, but later I will learn F. So this is only a planning component in my whole algorithm. Okay, if I know F, I can find a way to construct the feature for Bellman backup.
And how do you find those features?
It's right here, the second way. It's since this is Gaussian kernel, I can rewrite this part with the random Fourier feature, which means I sample omega according to the Gaussian distribution, and the phi omega f here is actually sine cosine omega transpose f.
So what are the features?
The features are sine omega transpose f, cosine omega transpose f, and sine omega transpose f.
So X has to be a continuous number, I guess.
So here X denotes F. So I should clarify this F plugin here. So it gives me the features.
Anyway, so and what in your features, what is omega?
Omega is random. It's some random number. It's sampled from Gaussian. I should sample, let's say, D. Then it will be D dimension random features.
So you sample omega D times, and you have D features. And are you claiming that you can guarantee that whatever your samples are, you will represent the system exactly?
Not exactly. That's approximately.
So if D is large with high likelihood, you can approximate it. And if your weights are good, you think you can approximate it closely.
Yes.
Well, but that's the old thing. That's, you know, if you take enough features, you can approximate anything. So that's just the old thing.
I think here I should distinguish two things. First one is universal property, which means once you give some infinite stuff, you can approximate the smooth function arbitrary. Well, that's called universal. I agree, that's true. But here we are just trying to say, with some specific design, we can show the Q function lies in this space, even it is not smooth. So these are two different stuff.
Okay, thank you very much.
So
can I ask,
here,
just a quick follow-up question to make sure I understand. It's the logical background person's question following up on Rich, where I understand the distinction that you make between model free and model based, because your colleague Dale Sherman has tutored me well to make sure I pay enough attention to understand the difference. But I take Rich's question to be about whether or not the features you're approximating in the model-based one are any easier to find alignment with the real world or not. So I appreciate being able to do this transposition to that, your use of the term model-based as a optimization function that's well behaved. That's one of the ways I think about it. But is there something you can give me that helps me understand not just the technical better behavior of that formulation of what you call model-based, and connect it to a world? So if I'm looking at images and 3D or 4D images used to build a policy for reinforcement learning for autonomous driving, whether I use your model-based or model-free system doesn't give me much insight in how to choose the alignment between attributes, like Rich asked, and the world that I'm trying to model. I think maybe the use of the word model is a little different too. Is that true?
I would say no, because here the model refers to the dynamics, which means we specifically for example this model, okay, right here.
Okay, so that's the intuition you have, is that the dynamics of this reformulation still refers to the dynamics of the world in some way. It just, we all know it's hard work to get that alignment and confirmation. So that's not the issue. Okay.
Okay. Yeah.
Okay.
This is referred as a model. Yeah. In reinforcement learning scenario.
Okay.
Okay.
Thank you.
Okay. Seems like we are clear. Here we construct one linear feature such that it can approximate with finite dimension. It can approximately represent the function space of Q, and if it goes to infinite dimension, it is the space of Q function. And now we also know that if we can back up in this function, we are perfect, solve the problem. And then that's for planning and how we can do learning. And learning actually is a balance between the exploration versus exploitation. Basically, here is a very common Thompson sampling algorithm framework for model-based reinforcement learning. Specifically here, F that denotes the dynamics we are trying to do. We are trying to play with, and we estimate a posterior among the dynamics. But when we do planning, we use backup in that linear feature space. So this is significantly different, I think. Otherwise, there's nothing different compared to the common model-based reinforcement learning. Okay, here I want to emphasize that this is compared to the existing model-based reinforcement learning, although the exploration versus exploitation is kind of like similar, follow the Thompson sampling, the planning component is significant, which means we can explore a lot of information just besides the sample from the dynamics. This one actually is very helpful because we believe sample is like only provided local information of how dynamics should be evolved, while the representation here actually provide more information beyond that. Okay, and we definitely can provide some regret bound with respect to the eluded dimension of the whole F dynamics and also the horizon of the planning part. Yeah, that's the detail of this one. I will just omit here. And if you're interested, please look at our paper. And okay, here's the empirical part. So we compare with the most the recent state of the art model-based reinforcement learning algorithm like ME, TRPO, and PATH-RS, PATH-CEM. Meanwhile, also because we claim this is representation based, we also compared to the deep version of successor feature, and we can see on all the module code environment, our method actually significantly dominates the rest of them. But I don't want to hide the results here. Let's see here. This is compared to the model free because we claim this is a combination of model free and model based. So we expect it to be better than both model free and model based. And the thing is, it's not that significant compared to model free, the state of the model free, for example, the SAC. We can see the result here. It's not as we expected. So we conjectured why it looks like this. And actually, here's maybe the reason we thought it should be. Why is we consider infinite dimension linear approximation? And when we compute it, it's only finite. So we believe there must be some approximation error introduced in this step. And second, because the whole algorithm based on a posterior, Thompson sampling, which is sample something from a posterior. And this part is also introduce some approximation error. And the third one is in our model, we use Gaussian noise in the model dynamics. So we believe this three thing may be the major reason why this algorithm is not performs well. But before we go to next step, I want to emphasize the take-home message. At least the linearization makes the nonlinear dynamics potentially solvable, which roughly which we believe which is important in progress on the nonlinear MPC. And another one is linearization actually breaks the model free and model-based RL, because we can extract the important component from model for model-free component like Q function. And then let's go back to see how we can deal with these three potential gaps, which makes the algorithm perform not well in practice. Okay. So basically, I want to still go back to the linear model, but instead of infinite dimension, we want to see whether we can find a phi which is finite dimension with finite dimension to approximate the whole transition operator. So actually it's not easy to do that, because we believe this is unnormalized conditional density, and if you apply the maximal likelihood for it, it is intractable, because you need to make sure this is a distribution, which means you need to emphasize for arbitrary state and action, integration of next state is always 1. It's not easy to do that. And second, if you really want to get some bound, you also need to enforce the mu function, mu feature here follows some they call normalization condition, which means and this is also not easy to make sure in practice. And finally, once you learn the function phi here is changing, so exploration with that changing phi is doable. Computation is doable, but it's difficult to provide a theoretical bound for that. Okay, let's see how we can bypass this too difficult here. First of all, we want to get the boundedness of mu part. So here we introduce the probability PS prime and times with mu S prime. And then we can see the boundedness actually is easy to obtain if the mu S prime is bounded. And this one is actually easy, because we can always parameterize mu S prime here with some bounded neural like sigma. So that means the second condition here is not a problem if we modify this linear MDP a little bit. And then let's see how we can bypass the MLE. Actually, we provided 2 strategies to bypass that. One is we use the contrastive loss, basically noise contrastive estimator. Oh, this is a very old estimator provided by Apple. I think it's 20 years ago, basically. Nothing new here. Basically follows definition of the NCE. We do estimation of both phi and p and mu. Both phi and mu here. P we provided. Okay, so this is one way to bypass the MLE. Another one actually is I want to highlight here, which is recall that the model basically is doing finding the singular vector of the transition operator. So we can use some SVD formulation to extract the phi specifically. So consider this as a matrix. So the formulation here actually is the variational formulation for the singular value decomposition. It is easy to solve if this is tabular, so we can always estimate this and plug it in to solve the phi function. But it's not easy if state and is continuous. So what do? We do some algorithm algebraic manipulation, basically introduce dual function and do some changing here. Eventually, we obtain the third line. Basically, we can claim this line is friendly to computation because every term here can be approximated by Monte Carlo approximation. That means we can use stochastic gradient to solve this object function for learning phi and mu prime. Okay. And with that, I think I answer the Rich's questions. If I can find a finite dimension space phi to represent the transition operator. And then I don't want to say approximately. So if I can solve this algorithm perfectly, I have the finite dimension linear representation for my transition operator, such that my Q function can exactly represented in this space. Okay, and also actually based on this kind of understanding, it is also related to the well-known successor feature. I will explain later, but now let's focus on this algorithm. Okay, now we can construct the whole algorithm, which is actually iteratively refine the feature and refine the policy. The algorithm looks like this. We first collect the data according to previous policy and uniform action for one step. And we plug this, we augment the previous data set. Okay. And we use either the noise contrastive estimator or the SVD estimator to get the phi function. And we calculate the UCB bonus. We do the policy optimization with this Bellman recursion with the bonus here. And with that we get another policy, and we use that policy to do the data collection and refine the representation, and it's iterative and so on and so forth. And we can provide this sample complexity of the whole algorithm. Actually, it is polynomial with the dimension of D, which is a feature, and also the okay. Here's some problem, which is we can only provide the guarantee for finite actions. So it depends on the action square, size of the action square, and some other parameters. Okay, now until now, I was wondering whether there's any questions.
Well, of course, I've got some more questions.
Definitely.
Your sample complexity doesn't depend upon the size of the state space. Does not depend on the size of the state space.
No, it depends on the size of the function space, not depends on size of state space.
Yeah, so that's a yes. It does not depend on the size of the state space.
Mm-hmm.
But doesn't D, the D actually depend on the size of the state space, because the D has to be big enough that you can exactly represent the system or nearly represent the system, and that will depend upon how complex the system is.
The answer here is maybe, but we believe there is some latent low rank structure in the system. So if we can find that D, it's not dependent on state and action.
I see. So that leads to my next question, which is, yeah, you believe that you can approximate things exactly, and I've got sort of a slogan that if you really are if you're genuinely doing approximation, you have to embrace the idea that you cannot do things exactly. You cannot approach the exact solution.
I agree. This thing I said it can be represented exactly of the Q. It's just because I want to prove this sample complexity. But I believe definitely it cannot in practice. That means we still have some further work to do, at least for the analysis part. But empirically, we test it. Although it's, as you mentioned, it's not represent exactly, you will see the performance of this feature is still good enough.
I'm sorry, but you seem to be going back and forth on this. You said there's going to be a low dimensional subspace that will enable you to do it exactly. Now you're saying you're not going to assume that.
I mean, in the theory of proof, we assume it. But practically, I agree with you. In some cases, we can find this such kind of space, but in other cases, we don't know.
Okay, thank you.
Okay, any questions? And now I think we can safely put every algorithm in one table. We compare to both model-based reinforcement learning, model-free reinforcement learning, and also our previous algorithm and this new algorithm we call speeder. We can safely say this algorithm basically beat the rest of the algorithm, no matter whether it's model-based or model-free, with large margin. In most cases, this is logical environment. And this is the final results, but let's see how it performs in terms of the conversion speed. The blue line actually is ours, and the red line which is a major competitor, which is soft actor critic. This is on the demand control environment. This sometimes is difficult because the reward is very sparse. For example, Hooper and humanoid. And we can see that the algorithm performs significantly better in terms of the conversion speed. It's converged very quickly, basically. And until now, I think I finished the major component of the talk. And next, actually, I want to show another interesting relationship, which is between some people call it a skill learning. We here do the representation learning, but actually we know this there's corresponding between pi and the q. That means we can build a bridge between the skill set learning and the basis we used to construct the q function. So we also do some preliminary tests about whether this, once we learn it offline, and we use this 5 feature for downstream policy construction. And you can see we compare to the existing state of art called skilled and OPA and the trail. The blue one is ours. It seems like our algorithm is also kind of like comparable at least, but sometimes better. It shows that this feature we learned is not only can be used in online setting, but it can also used as a skill basis to reduce the difficulty for downstream imitation learning. Okay, I think this almost reached the end of my talk. I want to emphasize that this linearization basically enabled us to do efficient exploration and efficient planning, and it's also a good way to bridge model-free and model-based reinforcement learning. While we definitely have some future direction, for example, we hope we can show some better analysis without exactly representation kind of condition. And we hope we can generalize this kind of idea to POMDP, which is more practical. And okay, finally, this is something I want to echo. So Rich and Bowling and other people just provide a paper about Alberta plan. I think what we are doing actually is also one part of the Alberta plan, which is we want to build the bridge between the value function learning and the transition model for planning this kind of interaction. Okay, here's our the paper I covered today, and this a free lunch from noise. Actually, it's the infinite dimension part, and the making linear MDP practical and this SVD decomposition. Actually, it's about the how we can find a finite linear representation for the transition operator, and do the efficient exploration and planning. We have more results actually, thanks to Chen Jun. We have more general model beyond the linear MDP, but while still have the linear structure, and basically more results on the way. And thanks and questions. Oh, actually, I forgot one thing here. This slides. I just want to bring a connection between the spectral feature to the success feature according to the spectral view. Here we can, although the successive feature actually defined according to the backup, but actually it's essentially doing a SVD decomposition for a very special variant of the transition operator. Meanwhile, similar to some proto value function and spectral state aggregation and so on and so forth. While we also do SVD, but we not do state transition. We do state action state transition. So that gives some benefits because we don't have any dependence of the to the behavior cloning behavior policy to collect the data pi here, which means the phi actually is invariant to any policy. Okay, I think that's all of this talk, and yeah, welcome any questions.
So the point of the idea is to create representations for which you can represent things linearly.
Yes.
Now, but the only thing that I'm trying to figure out where these feature vectors, the feature representations come from. And the only, I queried you before about that, and you said it comes from knowing the model. Of course, if you know the model, then you wouldn't need to make features at all. You just know the model. And you're also saying this is applicable to the model-free case. So, can you give us some intuition, really, about where the features come from?
Okay, I think there are some misunderstanding here. I said this section, if I know the model, I can do the I can extract the features here, right? But later, for here, I said I can use learning to refine the posterior of the dynamics. And then I can use Thompson sampling, which means I can sample from there to get one model, one sample of the model, and do the infinite dimension linear representation.
So I guess I didn't understand that part. I was wondering if you could give us some intuition about where the features come from when you don't have the model.
This part, I didn't get it. I always learn from data for the phi.
And how can you use the data to generate features?
Okay, let's see the specific cases here. I actually use the third line for my optimization. The data actually is collected according to some distribution, S, A, S prime. And I optimize this object function to basically essentially is doing the SVD of the model, but I use sample, extract the phi feature here. And this will be used in my later algorithm for planning and exploration. Is this answer your questions, Rich?
Both, if I might, could I just clarify a bit? So the outcome of this learning is essentially a neural network that maps SA to a feature vector. So he's sort of learning the features through a neural network optimization.
And what's the objective of this optimization?
Yeah, this third line, this is my object function.
Okay, but could you tell me, you know, in some intuitive sense, and I don't really
Okay.
And any of that actually.
So this one is difficult to understand what it's doing here. But actually, as I proved, it is essentially doing this object function. This is my actually. What is this?
Take that objective function. The phi is a vector. I believe that's an inner product that you're writing down. But I don't know how you take an inner product of a vector with a probability. I'm just confused about the notation. What is it? Can you say in words what is the idea?
The idea actually here is I want to factorize. Let's make it tabular case, okay? That helps you for understanding. The idea here is if I have this this matrix, okay? What I essentially want.
You don't have that matrix because it's a model-free case.
Yeah. But I want to give you an intuition what it's doing, what it's trying to do. I don't. This one is just for understanding, but this one is for my literally computation. What is I'm doing in my code. So I think this is not easy to understand. So that's why I want to go back to the origin. Why I want so I can explain the meaning of phi.
Okay. If you could explain that in some intuitive way, I'd appreciate it.
The intuition here is that I want to factorize P. Factorize according to the SVD of this transition operator. And this object function is a variational formulation for SVD decomposition.
Bo, could I attempt a bridging explanation here?
Sure.
Let's literally think of the tabular case as you said. So we have an S by SA matrix P. Happens to be a stochastic matrix. Of course, later on we won't know it, but for the time being conceptually, assume we have the full stochastic transition matrix. Then what this first line is saying is we're literally trying to find the right singular vectors of that transition matrix. If the transition matrix is low rank for some reason, then we would get like a set of right singular vectors that isn't square.
So you're trying to find feature vectors which will enable you to accurately match the transition probabilities.
Yes.
Yes.
Which makes good sense in the model-based case. But if you don't have that matrix, how do you come up with these features?
Yeah, actually, we never exactly solve this one. We do some mathematical derivation such that in my code, I use object function as the third line here. Okay.
So can you say intuitively what you do to find the features?
The feature intuitively is, as Dale mentioned, it's write a singular value of the transition operator. But as you know, as you also notice, this is never doable. We just find a mathematical equation for that. For the third line, it's difficult to explain because we introduced dual function here. What is dual doing is not very clear yet.
I think I can explain it.
Yeah, okay.
Should we give it a shot? So once we're looking at the third line, right? So we just assume we're focused only on phi for the time being. So we have some big neural net consumes state action pairs and produces some output vector. It's got a bunch of parameters. And we literally have an objective here, which is like a differentiable function that, we would just follow the gradient ascent, to optimize the parameters of that neural net to maximize this function. Now, this function has one problem, which is you can see there are these expectations. So literally what happens is you sample from the distributions, right, that are sort of part of those expectations. So you take a sample, you take an empirical approximation of those expectations, and then follow gradient ascent in that actual concrete function, and then resample. So Bo set called this stochastic gradient. So resample, take some gradient ascent, and then resample, so on and so forth. And you would wind up optimizing the parameters. If you sampled enough and iterated enough, you would hit a fixed point, which would solve that third equation.
One thing that would help clarify for me, if you could say, do you do this on a sample by sample basis, or do you collect a bunch of samples in order to estimate the expectation, and then you do something on the whole bunch of them?
I do sample based. It's a mini batch. I sample some of them and do one gradient update with respect to both phi and mu prime, and then I collect another batch, small batch. It's like training neural network.
So you don't do it one by one. You collect a batch.
Yes.
You do an update on the batch.
Mhm.
Okay, well, that helps a little bit. Thanks.
Yeah. And any more questions? Yes, sounds great. And yeah, I will stop sharing my screen.
All right, thank you so much, Bo, for the presentation. We'll post up the video recording there once it's all professionally edited up.
No problem.
All right, have a great afternoon, everyone. Thank you.
Thank you. Thank you, everyone.
Bye.
Bye.
Thanks, Bo.